This is November 2013. Question 1. State the main advantage of a single-phase synchronous motor compared to a single-phase induction motor. Well, synchronous motor means that it turns at synchronous speed. It's always at the same speed, so constant. So a synchronous motor rotates at a constant speed independent of the load. If we load up a single-phase induction motor, then that speed is going to change, whereas the synchronous speed of a synchronous motor is always the same. Two reasons for using the reduced voltage starting for three-phase induction motors. So we don't want to put the induction motor straight onto a high voltage. So we reduce the voltage on starting, and that will reduce the starting current and reduce voltage fluctuation. It'll also limit the mechanical shock. Describe how the output voltage of a large transformer is maintained as the load changes. So as we know, as we load up a transformer, because the impedance of the transformer and the current flowing through the impedance, we'll get a volt drop. And so what we need to do is we need to have a tap changer to maintain the voltage. So we tap off at a different point of the secondary winding to increase the voltage. The term burden in the current transformer, that's the total VA that can be imposed on the CT. So it's the total load that it can take. Two methods of phase splitting used to provide the starting torque in a single phase induction motor. So a single phase induction motor won't start unless we got two phases with out of phase current. And what we can do, we can have a capacitor in series with the auxiliary winding or the start winding. We can have different winding impedances. So the split phase motor has two windings and they've got different impedances. Or we could have a shaded pole, and that will give us an out of phase current. Two devices that can be used to protect semiconductor components against the effects of transient voltages. Well, we can have any two of these: snubber circuit, MOV, freewheeling diode, RC, optocoupler relay, UPS. I would be remembering these two, the snubber circuit and the MOV. State two factors that determine the volt drop in a 400 volt final sub-circuit TPS cable. So when we're looking at volt drop, what are we looking at? We're looking at the material, because that will tell us that will give the resistance of the cable. Cross-sectional area, that will also affect the resistance. The load, which will be the current flowing through it, because V is I times R, so that's the I part. And length of cable, that's going to change the resistance as well. So these three are going to change the resistance of the conductor, and this is going to change the current. F, a three-phase squirrel cage induction motor is running fully loaded. State the main effects on the operation of the motor if the supply voltage drops. Well, if we reduce the supply voltage, then we're going to reduce the motor speed. And if the speed goes down, we get less cooling effect, and so the current rises until the overload operates. G, state the reason why a HRC fuse would be installed upstream of an MCB on a switchboard. So an MCB hasn't got the rupturing capacity of an HRC. So if we've got a very high fault current, a prospective short circuit fault current, then we need this HRC fuse in there that can safely interrupt that big voltage. So G there, the breaking capacity of the MCB is too low for the PSSC, prospective short circuit current of the installation. That could be one instance, or if the level is increased for some reason, then we might need to put that HRC fuse in. H, state would occur if a 230 volt single phase capacitor start motor that was running suddenly experienced a 50% drop in speed due to mechanical overload. So something's jamming, if you like, it's the speed has fallen and the protection has failed to operate. So the motor is going to stall and burn out. It's because we've got that less cooling effect, it's going to have more current and it's going to burn out the windings. I, two reasons why an RCD tester is used to test a PRCD. So what are the two things that we're testing when we're testing this? We're testing that it operates within the specified residual current limits, be that 10 milliamps or 30 milliamps or 100 milliamps. We're verifying that it operates within the specified time limits. So we're looking at the maximum current, the sensitivity, and the time. State one hazard that would occur when using a multimeter to measure output voltages in high pressure sodium vapor lamp control circuits. Now these control circuits are very high voltage, so we've got a shock hazard there, typically 4K to 10 kV. And damage could occur to the meter if the measurement is made during startup. So it's during the startup when the lamp strikes, we've got this very high voltage, and so we could damage a meter that isn't specified for those kind of high voltages. State one hazard that could occur if low pressure mercury vapor lamps, so our normal fluorescent tubes, are broken during disposal. Well, we've got injury from the glass and inhalation of phosphors contaminated with mercury. So there's small particles of mercury inside the phosphorus, inside the fluorescent tubes, and so we don't want to be breathing in that material. State one hazard that could occur when disposing of low pressure or high pressure lamps. So we've got a risk of fire and we've got a risk of chemical burns. State one hazard that could occur when operating an HID metal halide lamp with the lamp's outer envelope broken. So we've got problems with skin burns from the ultraviolet radiation, eye inflammation from shortwave ultraviolet radiation, and we've got exposed filaments that are a shock hazard. So any one of those. So if that outer envelope is broken, we're not going to get the protection that it normally gives us against these ultraviolet radiation, and also there's a shock hazard. Number two, we've got a earth fault loop impedance tester plugged into a 230 volt socket outlet in electrical installation. The socket outlet is protected by a 20 amp HRC fuse, high rupturing capacity fuse. State the reason why the earth fault loop impedance test is carried out at the socket outlet. Now, when we carry out the socket outlet, we're looking to verify that the fault loop impedance, so the impedance of this path and the path through the earth there, we've got a parallel path, is low enough so that an HRC fuse will operate in 0.4 seconds. So we want a low enough impedance to give us enough current so that the fuse will blow quickly in 0.4 seconds. Now, if we carry it out at the switchboard, what are we looking for there? We're looking to make sure that the braking capacity is rated to safely interrupt the prospective short circuit current flowing under fault conditions. So we're making sure that the HRC fuse has a high enough braking capacity. We've got a time current graph here, which is that bit shown there, and there's our HRC fuse, and there's our thermal overcurrent protection. We've got to describe what would occur if the motor was to draw a line current of 70 amps. So if we look at the scale on the bottom, it's a logarithmic scale, so it's not linear. So there's our 50, 60, 70. So how long would it take to blow? If we go across, about 1 minute. There's our minute time there. So the thermal overload device would operate within 1 to 2 minutes. So because that 70 doesn't touch the HRC fuse line, it's only touching the thermal overload line, that's what's going to happen. So within a minute, or within 1 to 2 minutes, that thermal overload is going to trip. If we get a fault current at 150, well, there's our 100 there, there's our 200. So 150 in a linear scale would be roughly in the middle, but it's where it's non-linear, it's gonna be slightly off, but it's gonna hit that HRC fuse there, and we're gonna go across here. It's gonna be a very, very short time, and it's only gonna be about 0.2 seconds. So it's gonna be a much faster operation because the HRC fuse is gonna operate. Part 2. Compare operating times of 70 amps HRC fuse and 150 amp HRC fuse. Demonstrate how the inverse time current characteristic occurs by using the operating times of the two fuses as examples. So what we're saying there is, as the magnitude of the fault current rises, so as more current flows, the time taken for the fuse to operate decreases rapidly. So there's not an awful lot of difference between those two currents there, but when you look at the time difference is much faster with the higher current. So higher current, much lower times to operate. Describe what occurs in electrical installation when a fault occurs in electrical installation and there is correct discrimination between the two devices. So when we've got correct discrimination, the protective device closest to the fault operates before any other protected device can operate. Question 3, we have to draw a three-phase full wave bridge. So we've got our 6 diodes. There's our diodes there. Just be able to draw this. This comes up quite a lot. So our 6 diodes all point in the same way with our 3 phases connected, and then our load connected. And the positive of the load comes from the cathode of the diodes. So traditionally we would draw these diodes going up. They've drawn them coming down, so that the positive is on the bottom there. If we reversed all of these diodes, then we'd have the positive at the top there and the negative there. It's quite a simple diagram. Just be able to draw that diagram. The ripple frequency, if we've got 50 Hertz input, then the ripple frequency is 6 times that 50 Hertz because we're getting 6 lumps out for every waveform, and so we get 300 Hertz, 6 times 50. 2 components to use as filters. Well, we can use capacitor, inductor, they say resistor as well. The resistor, you can only use it in conjunction with one of these two, but they would accept that. If I was remembering this, I would remember capacitor and inductor. 3b, we need to draw a voltage dependent resistor, so a VDR. That's what I would be drawing there, that one at the top there. They've given you a couple of alternative circuit symbols. The main function of the VDR, so it's to protect us against spikes, some high voltage transients. So things like lightning strikes or just high voltage developing. This VDR will go short circuit and take all that current and operate the protective device to save the sensitive equipment. So it protects it from voltage spikes. How does it do this? So it drops to this very low resistance, and it protects the equipment by shorting the spike to spike the instant it appears across the VDR terminals. So that voltage spike, that lightning strike or whatever, doesn't get to the equipment because this VDR goes short circuit and takes that voltage spike. And where do we connect it? We connect it in parallel with the supply to the equipment being protected. So you'll see it across the supply, across the phase and neutral before the equipment that we want to protect. Question 4, we've got a 230 volt transformer with a step down ratio of 20:1. So it's 230 volts, it's just a single phase transformer used to supply electric toys. The transformer has 2000 turns on the primary, so we've got this 20:1. The primary draws 2 amps when fully loaded. So calculate the number of secondary turns on the transformer. Well, the secondary turns is just going to be this primary turns divided by 20, which is what we've got here, to give us 100 turns. The secondary voltage, again, this is going to be 100th of this, sorry, not 100th, it's going to be a 20th of the primary voltage. So the secondary voltage is going to be 230 divided by 20. They've done it slightly different. They've put the 100 and the 2000. They've used the traditional formula, but I think you'd be okay with Vs is equal to Vp divided by turns ratio, and 230 divided by 20 gives us 11.5 volts. The volts per turn of the transformer, we could do that with the primary or the secondary. They've done it with the primary, and it's probably the right decision. So because they're the values they've given you. So if you use these ones, if you got this wrong and you did the volts per turn, then you'd get that wrong. So use the ones they've given you. 230 divided by 2000. So you've got 230 volts across 2000 turns. How many volts on one turn? Is going to be 0.115 volts per turn. The VA of the transformer, because it's just single phase, it's just going to be the volts times the current. So again, you can use the values they've given you. 230 times 2, we've got 230 volts on that primary. We're told there's 2 amps flowing, so that's 460 VA. State the main reason why the transformer is double wound. It's because we want to isolate that secondary from the supply. So it's a toy. We don't want it to be like an auto transformer where that primary voltage can appear on the secondary if there's a fault. So that's why we don't use the auto transformer for this application as of a toy, because in an auto transformer there's a physical connection between the primary and secondary, and under fault conditions or incorrect connections, so if someone connects it up wrong, we can get dangerous voltages can appear on the secondary. So we could get that 230 volts appearing on the secondary voltage, or even more actually. Question 5, we've got a new 3-phase water heater in a dairy shed. We've got 3 230 volt 400 volt elements, each with a resistance of 30 ohms. The heater can be connected in star or in delta. So these elements can run at either 230 volts or 400 volts. We've got 2.5 mil TPS, and we've got a 20 amp rewirable fuse. And we're going to use calculations to show that star is the correct connection if the existing final sub-circuit cable and protection is used. So if we're going to use a 20 amp rewirable fuse, then we've got to make sure that the current that flows into that heater is less than 20 amp. So what we need to do is to show the current that would flow in star and in delta. So the phase current in star is going to be the phase voltage divided by the resistance of the phase. So in star we would be working with 230 volts, and the resistance would be 30 ohms. 230 divided by 30 will give us 7.67 amps. So that's the phase current, and in star the phase current is equal to the line current. So our line current is going to be 7.67. So that would be okay for a 20 amp rewirable fuse. In delta, the phase current is going to be the voltage on the phase, which in delta is going to be 400. So 400 divided by 30 gives us 13.33 amps. But that's only the phase current. The line current is going to be √3 bigger than that, because IL is IP or I phase times √3. So 13.33 times √3 gives us 23.1 amp. And obviously this is much too big for a 20 amp rewirable fuse. So the current drawn by the delta connection method is too large for the protection. So we would use star. Calculate the power consumed by the heater using the star connection. So power is √3 IL VL power factor Because they're resistors, that power factor is just going to be 1 unity. So we've got in star connection, our VL is 400. Our IL is 7.67 that we calculated up here. Times √3 times 1 gives us 5313.78 watts. State the simplest change that can be made that would allow the water heater to be connected in delta. So we would need a bigger rating of protective device, and we'd also change that rewirable to an MCB or an HRC. We wouldn't put a higher rated rewirable. We wouldn't replace it with a rewirable. We'd go with the MCB or HRC. Calculate the method consumed by the heater in delta. So we can use the same formula that we used here for star. We can work it out in delta. The thing that's going to change is going to be the current here, IL. It's going to give us a much bigger watts there, just over 16 kilowatts. Arguably, we could have just done this power times 3, because the power in delta is 3 times the power in star, and we would have got a very similar answer. So just over 16 kilowatts. Question 6. Draw and label diagram of a 230 volt single phase capacitor start, capacitor run induction motor. So there's our capacitor start. So there's our centrifugal switch, our starting capacitor, and our start winding. We've got our run winding there, and we've got our rotor in the middle there, and we've got our run capacitor there. So describe the operation of this motor from the time it's switched on to it reaches full speed. So when we first start the motor, the centrifugal switch is closed. The motor starts because we've got 2 windings connected together. The capacitance gives us good starting torque. When it reaches 75% full speed, this centrifugal switch will open. It will disconnect this capacitor here, and it will run on just the 1 capacitor on the run capacitor. That will give us a decent running torque. So we get good starting torque, and we get good running torque. State the main reason why a single phase capacitor start capacitor run induction motor would be used to drive a large air conditioning fan instead of a split phase motor. So a split phase motor doesn't give a very good starting torque. It also produces more vibration and noise. Doesn't run as smooth and as efficiently. So our capacitor start capacitor run would provide less vibration and noise for the air conditioning fan. Question 7. We've got a 400 volt 3-phase 2 kilowatt pump, including a switch, DOL, and final subcircuit. They've been installed but not connected to the switchboard. The order of connection to the final switchboard is from the switchboard to the isolator, from the isolator to the DL, from the DOL starter to the pump. Use the information to answer these questions. So we want to state the 4 tests using test instruments that need to be carried out to ensure the motor and final subcircuit are safe to connect. So with the testing procedure, first test earth continuity, then you're looking at insulation resistance, and then you're looking at testing the motor windings, and then correct circuit connections. The second part asks you to describe the tests that can be carried out with the motor disconnected. So for each of these tests, we want the test instruments, the test voltage, how the test is carried out, a test result that permits connection to the power supply. So we need the answer or the result that's going to say that it's okay. So you need to know these tests. These earth continuity and insulation come up all the time. We've got the addition of the motor winding test. That's just measuring the resistance of each winding and making sure they're very similar. Earth continuity, we're looking for that 1 ohm or less using an ohm meter. And with the insulation resistance, we're looking at 1 mega ohm or more using insulation resistance tester on 500 volts DC. Question 8, we're going to draw a 230 volt RCD used for personal protection, and we're on a class 1 equipment as the load, which we've got down here. We've got the toroid, we've got the phase conductor, live conductor and neutral conductor flowing through this, and then we've got the coil here, the sensing coil, and the tripping device. So if this sees an imbalance between the two, it will trip here and these will break these contacts. And we've got a test button here between live and neutral with a resistor in there. So what that will do is when we press that test button, we'll get a small leakage of current because of this resistance, and this will set up an imbalance within the toroid, which the tripping device will see, and it will trip here. So they've drawn the class 1 equipment there. State the minimum permitted rated residual current of the RCD installed. So personal protection domestic is 30 milliamps. Medical, as soon as you see medical or nursery or things like that, 10 milliamps. Property, 300 milliamps. Why we can't use AC RCDs in New Zealand? It's because they don't have this residual pulsating DC function. So we want to test on DC, that constant current. The phase neutral on the supply side of a single phase RCD have been transposed. So is this going to affect the operation? Well, the RCD isn't going to care. Is it going to operate? Yes. The RCD detects the imbalance regardless of the polarity of the supply. So it doesn't care which way around the phase and neutral are. If there's an imbalance there, it will operate. Would the RCD operate if there was a short circuit between neutral and earth? I'd say yes, because it's looking for an imbalance, and if that neutral current is leaking to earth, then there's going to be an imbalance between phase and neutral again, and so it's going to operate. Different types of RCD, so there's P, the portable residual current device, the residual circuit breaker with overcurrent protection, and the socket residual current device. A main switch for a 400 volt 50 Hz three phase supply is rated at 20 MVA, mega volt amps. Calculate the maximum short circuit current that the switch can safely open under fault conditions. So we've got an MVA rating. We can work out the current using this formula that VA is √3 VL IL, and we're going to transpose for IL. So IL is going to be the MVA divided by √3 times VL. So there's our √3. We're told it's 400 volts. So it's 20 times 10 to the 6, because this mega is 10 to the 6, and that gives us 28.87 thousand amps, kiloamps. So extremely high fault current that it can interrupt. Just to go back, question 9a, MEN distribution system. 2 technical reasons why the neutral conductor is earthed. So we've come across this lots of times before. It's earthed so that we can limit the voltage to 230 to earth under fault conditions. It limits the voltage between neutral and earth to around about 0 volts. And it ensures that under fault conditions, the voltage between any earthed metal and the mass of earth never rises above about 0 volts. So it keeps that at 0 volts. A 230 volt class 1 dishwasher is used in an earthed situation. Explain how effective earthing of the metal frame of the dishwasher provides protection against electric shock. So it's going back to this, that if there is a fault, because it's earthed, it will make sure that the voltage on the frame never rises above this 0 volts, because the resistance of the earthing conductor does not exceed 1 ohm. So as long as we keep this earthing conductor to a low resistance, then this voltage on the frame never gets above 0 volts. It's when we've got a very high resistance in the earthing conductor, and we've seen that in some of the calculations, that the protective device doesn't operate, we get current flowing and we get a shock hazard. Two factors that limit the prospective short circuit current and in an electrical insulation. So what's going to limit the amount of current that could flow under fault conditions? Well, it's going to be the capacity of the supply source. It's going to be the transformer impedance. And it's going to be the circuit impedance, or the length of cable run, or the distance from the transformer to the switchboard. So all of this is going to affect the impedance of the circuit. So it's the transformer impedance, the circuit impedance, and the capacity of the supply. So the capacity to push out the current, and this to try and stop the current. State the main reason why Class 2 double insulated electrical equipment is not required to be connected to protective earthing conductor. So we don't earth Class 2 equipment. And why don't we earth it? Well, because there's this supplementary insulation between the basic insulation and any metal that could become live under fault condition. So we've got two barriers from any phase conductor and any metal that someone could be touching that could become live. So not only have we got the insulation of the cable, we've got this secondary. Under fault conditions, it's more likely that a PEC would liven the frame of the appliance rather than the insulation breaking down. So you could answer it that way, that if we put that earthing on, it would make it more dangerous, basically. So we don't put the earthing on because we don't need it, and if we did, it would make it less safe.